Okay, now, so this was the tree search, and now we are moving towards the graph search. So in the tree search, we have seen that there are repeated paths. Repetition is there. So due to that repetition, normally we cannot reach on the goal node. So there is a need to remove those repetition, and then we can reach on the goal states. And here, this is the graph search in which we have removed that repetition. So for that removal, we introduce a new queue that is called explored set. Okay, frontier is also a queue, and explored set is now another queue. We will introduce another queue, uh, and the name of that queue is explored set, and that will contain what type of nodes? The nodes, for example, this node Arad, we already expanded. So this node which is expanded, this is expanded, and these are the new nodes generated. New nodes generated. So these new nodes, the nodes which are expanded, which are in gray color, you can see, we will store these nodes in explored set. And the nodes which are generated, these green ones, we will store them in frontier, in the graph search. Okay. So explored, we will introduce a explored set in which we will store expanded nodes, the nodes which are visited. We will store them. So and there is a condition that the generated nodes, you can understand the green color in the tree, the green color nodes in the tree. So newly generated nodes that will match with the ones in the explored set. So we will match these newly explored nodes, newly generated nodes, with the nodes available in the explored set. We will match them, we will compare them, or with the frontier. And if it is matched, then we will discard them, we will remove them. Let's see how we will do that. So this is the function, and the name of the function is graph search. We are passing some problem into it with all information, and it will return a solution of failure like the previous algorithm. And then here we have a statement: initialize the frontier using the initial state of the problem. This line is again same. This line and this line is again same. Initialize the frontier. So we have the frontier. Okay. And here we will initialize it with what? Arad. Because Arad is the initial state, So initialized, and then initialize the explode set to be empty. And then we have explode set here in explode set, It is what? It is empty. I'm not writing anything. And then we have a loop, and we have all these states under this loop or in this loop, And then here, so this is a new line. Initialize the explode set to be empty. This is a new line according to that previous. Okay, then all the lines which are bold here, these are the new extra lines that we added in this algorithm. The rest of the lines which are not bold, those are the old lines which you already saw in that research. So now here we are checking if the frontier is empty. No, it is not empty. We have something there. So then what? We will move next, choose a leaf node and remove it from the frontier. So, okay, we are choosing and removing it. And now in the node, I have what? I have this node in the, I have this node in the node variable. I'm not writing it. I am keeping it in mind, So I am highlighting with this arrow. So this is the node which is in the, after this statement in this node variable. And then I am checking that this node is a goal? No, it is not a goal because the goal is Bucharest. So this condition is false and I will reach here. Add the node to the explore set. So now add this. Add this node to the explore set. Okay, I am adding. I am adding. And then expand the chosen node. Expand the chosen node. So this line is now finished and now I am here. Expand the chosen node. So what is chosen node? This is the chosen node with the arrow. And the arrow is highlighting that. Arad. Expand the chosen node. And what are the three options according to the map? According to the map. So Arad has what? Three options, which you are seeing also here in the tree, huh? Sibiu, Timisoara, and Seren. So expand the chosen node. If I will draw a tree, you can see something like that. Okay, expand. And that is what? Sibiu. And then what? Okay. Timisoara and Serenda. Serenda. Normally, for example, why I'm calling it Serend? Because this is a European country, and normally in Europe, I already said to you that people are saying ZS and SZ. Huh? Similarly, like in Germany, is there any person in the class from Germany? Hmm? So anyhow, leave it. You can call it anything. So expand the chosen node. So I have expanded. Add the resulting nodes to the frontier and add these resulting nodes S, T, Z, whatever it is. It is, for example, S is Sibiu, T is Timisoara, and Z is what? And Z is what? Serent. So I have add the resulting nodes to the frontier. I have added. And now you have to add only if, sorry, uh, I didn't read this condition. This condition is also with that condition. Okay, one line, but there is no space, so that's why it is written in the next line with the indentation. Okay, which means that this line is after this. Okay, it is not a separate line. Okay, so sorry, I have added, but let's see if we have not violated any condition, then it would be okay. Add the resulting node to the frontier only if not in the frontier or in the explore set. So Sibiu, before this addition, these were not here in the frontier, huh? And frontier was empty before the addition. And here explore set has only Arad, huh? So when Sibiu, Timisoara, and Serend, these were not here in the frontier, or also not here in the explore set. So that's why then I can add the resulting nodes to the frontier, and I have added. Okay. So now what? Move on to this loop again and check. If the frontier is empty, no, frontier is not empty. You have new items there, new nodes there. Choose a leaf node and remove it from frontier. So, okay, I'm choosing this Sibiu and removing it from frontier. Okay. And then now my goal is what? My node is what? This Sibiu. Now my node is what? This Sibiu, huh? So this node is a goal. Is a goal? No, it is not Bucharest. Then I will come here, add the node to the explore set. Add this Sibiu to what? Here, explore set. So you are adding this Sibiu here. So this is done. And then this line, expand the chosen node. Expand now this Sibiu according to the map and add the resulting node and whatever the next nodes, you have to add them in the frontier only if they are not already available in frontier or explore set. So okay, let's see that. So according to, so now I am expanding this, and for example, this is first one, Arad. So okay, I'm checking that Arad is here. So okay, I'm expanding it, and I'm saying okay, Arad. I'm saying it Arad. So expand the chosen node. So now I am checking that this arad is available in this frontier. No, it is already removed. It is not available in frontier. And this arad is available in the explode set. Yes, it is available. Yes, it is available by checking this condition. It is when it is available, then what? Expand the node, add the results only if this condition fulfilled. And arad is already there, so it means that I will not expand it. Okay, because it is already there in the explode set. According to this condition, I can only expand or add which will not be in the frontier or explode set already. So that's why now that repeated state we are not considering in the graph search, because it is already available in the explode set. And now what is next? Okay, now I can take this already. So check this already. So you are in a wrong class, huh? So anyhow, so but I was saying already. Already is our next step. So expand. So I am expanding my CPU with already. With already expand the node, adding the resulting node to the frontier if not available in the frontier explode set. So already is here. No, already is not here. Already is here. No, it is not. Then okay, expand and add. So add, and then here I will add also in the frontier. I have expanded and I also added into the frontier according to this condition. And now next, what is next? For example, Rimini Kuvilcia. And similarly Fagaras. So now I'm checking them together just to save my time, huh? Rimini Kuvilcia and Fagaras. So expand the chosen node. So Rimini Kuvilcia, is it available in the frontier? No. Is it here? No. So then what? Expand then. Rimini Kuvilcia is there now. And add it in the frontier. Similarly, Fagaras is here. No, it is not. Here. No, it is not. So then what? Expand it. Expand it. And add it here. And in this way you will go on. And in this way you will go on. What is next? What is next? What is next? So now this is finished. You will go again to here. Frontier is empty. No, we have sufficient node. We have sufficient nodes there. Choose a leaf node and remove it from the frontier. So graph search. If you will go like a depth first search, then you will select this already next. Then you will select this already next. Okay. So already. So now this is already selected. Already is selected. You can also go with this order, but leave it because we want in the beginning, we want to be as simple as possible. Okay.
It's like a queue, so first and first.
Yeah, I said it is a queue because in the next algorithm, we will consider it as a queue. But here we are considering it like an array. Okay. So this is the beginning. So that's why I'm not putting you in complications. But in the next, for example, depth first search, okay, when it will come, it would be like that. When breadth first search, it would be like that. Okay. Then I will say that it is a FIFO or LIFO or whatever it is. Okay. Then I will change the strategy. So that's why we have different searches around us because every strategy is different from the other strategy. So anyhow, so now we can select the already. Okay. Similarly, for already, what are the options? Previously syringed, and the next one is, I can change the color. So what are the options? This one and this one. These two options for already. Syringed and CBU. Okay. So we have selected Frontier is empty. No. Choose a leaf node. We have chosen already. This already is a goal. No. Add the node to the explore set. And here we are. Sorry. We have to change the color again. So we have to add this already here according to this statement and expand the node. First is, for example, Serind. Serind is available in Frontier here. This is Serind, huh? So Frontier, it is available. So it means no expansion, no addition, huh? So you can expand, but it is not the part of the tree, huh? So it means, so for Serind is the path which is going back in the map. So that's why we will not add. We will not add because it is already available there. And then what is CBU? So check that we are here on this condition. So check that this CBU is here. From here it is removed, but here it is available. So it means that CBU, it is available in the explored sets. So we will not add, we will not expand. Okay. So already will be empty, huh, in the tree. And then what? So if we are moving like a depth first search, then we will execute this RV, huh? Because this is, we don't have any further things here. So then according to the depth first search, we will go the node with the parallel. So we will select this RV. So okay, select this RV. And in the map, what are the options available for the RV? So if you will see, for RV, this path, and this path is available. Okay. Sibiu, Craiova, and Patisti. These three paths are available. Sibiu is the path which is going backward, so maybe it will not happen. But this Patisti and Craiova is the new. So according to the graph search, these will be added. Huh? According to the algorithm, we know that. So we are going there. So RV is selected. Where I am here, choose a leaf node and remove it from the frontier. Okay, RV is selected and removed. And then we are going to remove it from the frontier. Choose a leaf node. Okay, selected and removed. And then we are checking RV is a goal. No. Then what? Add the node to the explore set. And here we are adding RV. Added. And then expand the chosen node. Add the resulting node. And what are the options with the RV? Maybe Sibiu, Patisti, and Craiova. Huh? So, okay, first I am taking Sibiu. I am executing this condition. So now I have a Sibiu. Sibiu is in here. No, it is not. Here, yes, it is. So I will not expand, not add. And then what? Then what? I will take the next node, which is what? So RV, Patisti, and then I will take what? Patisti. And then I will check Patisti is here. No. Patisti is here. No. If it is not, then expand and also add it in the frontier. And then what is the other one? Craiova. So Craiova is here. No. Here. No. So if it is not, expand and add it in the frontier. And now, according to the depth first search, what is the next node that will execute? According to the depth first search, what is the, so I will go there again to the loop. But according to the depth first search, what is the next node that will execute? Patisti. Okay. Patisti, in the tree, it is Patisti, yeah? It is giving you the guidance. It is giving you the guidance. This tree is giving you the guidance. Otherwise, from here, you will not know. Okay. So anyhow, Patisti is the next. Patisti is the next node. And according to the map, what are the options available for the Patisti? Let's see that. So this one, RV, Craiova, and Bucharest. You are almost reaching at the goal, huh? So RV, Craiova, and Bucharest. Okay. Keep these in your mind and then here. So we are again in the loop. Frontier is empty. No, choose a leaf node and remove it from the frontier. Okay, Patisti will be selected and removed. Okay, Patisti will be selected and removed. This Patisti. Now, this Patisti is a goal node? No. So then what? Add the node to the explore set. So I am adding this Patisti here. Sorry for this color. Huh? This is something. Yeah. It's okay. Okay. So Patisti is added here. And now the last, expand the chosen node, add the resulting node to the frontier only if they are not available in frontier or explored. If that node is not available in the frontier or explored, only then you can add or expand in the tree just to make our tree clear. So Patisti, first it is going backward, which is RV, huh? Which is RV according to the map. But first it is going backward RV. So I am checking now. RV is available here. RV was available, but it is removed. So then check it here. RV is available? Yes, it is available. So then I will not expand, not add. And what is other? Craiova. Craiova is available here? Yes, it is available here. This one, see, Craiova. So if it is available there, I will not add, not expand. Okay. And then what is the next? Bucharest. So Bucharest is available there? No. Available there? No. So then what? I will add it here. I will expand the tree and then I will add it and I will add here in the frontier according to this condition. Now I will go again. And then I am checking frontier is empty? No. Choose a leaf node and remove it from the frontier. According to the depth first search, which node I will execute? B, Bucharest. So I will execute this Bucharest now. So choose a leaf node and remove it from the frontier. So I am choosing this Bucharest and removing it from the frontier. And then I'm checking this node, this node. This is a goal. Yes, Bucharest is a goal. If it is a goal, return the solution. Return the solution. And what is that solution? That you are reached on this state. Okay. That Bucharest is the goal. So then return the solution. So we are going out of this whole algorithm. We are going out of this whole algorithm with the solution. And what is that solution state? Bucharest.
Solution is explosive.
No, solution is the Bucharest. There is no path in there is no, for example, path that is available to you. You can let's see from Arad to CBU and then Oradi and then Ribuku will see and Patisti. Let's see that if this is the path, check that. Okay. We were going from Arad to what was that? ARSOR. Arad, Sibiu, Oradi. Huh? So Arad, this was Sibiu, and then Sibiu to Oradi. Here, huh? And then what? Arad, Sibiu, Oradi, RV, and Patisti. RV is here, and Patisti is here without these lines, huh? So that explored set is not giving you any information, okay? And in this algorithm, we are not storing the path from the initial state to the final state. This algorithm is giving us only the goal state. If you reached, it will give you the Bucharest. If you will not, it will not give you that, huh? So in the solution state, so here in the solution state, you have only the goal state. If you reached there, you don't have any complete path from initial to. For this, you have to maybe introduce some other variable to store the complete path or something like that. So here in this graph search, you have seen that repetition is now gone. Wherever repetition comes, we were not expanding, we were not adding those nodes in the frontier. Understood or not? How many students have understood this graph search? Raise your hand, please. Okay, good. This was a short algorithm, so that's why I didn't go on the whiteboard. Okay, but in the next algorithm, then when it would be lengthy, I will move on to the whiteboard. Okay. Now the rectangular. Uh, Now the rectangular grid. This is just an idea. If you have something like that, something divided into nodes like that, you can imagine this. But anyhow, let's see this first, that we have a grid here, and we can start from the mid of this grid. This is the starting initial state. This is the initial state. And if you will apply the graph search here, graph search is simply the depth first search without repetition, okay? Without repetition. So, okay, I will go have a look over here. So I started with the initial point, and then I am expanding, and I am checking that if these nodes are not in the frontier or explored, not already visited, then I'm adding in the frontier. And then I'm going according to the depth first search, and then checking each time that these nodes are new nodes. Then I am expand. I'm saying new nodes. New node mean not available in the frontier or explore set. So if new, I am expanding. If not, I am not. So this is the simple. So let's see that. So we have to start in this grid from the middle, and we have to expand the node clockwise. This is like clock, huh? Clockwise. And you can start from maybe from here, but you have to go clockwise. You can select any position. So this is the initial. If if these nodes were not here, imagine if you will have only this one node in the middle. If you don't have these four, then you have to expand it by yourself. Then what will you do? You will expand it like that first, and then clockwise. This is the second, then this is the third, and this is the fourth one, according to the graph search. Because these are the new nodes, not already visited. So that's why you will expand them all clockwise. Now you have a sequence. So now these green nodes you have in the frontier, huh? Now these green nodes you have in the frontier, and this gray you have in the explore set. Good, mashallah. So this is in the explore set, and these green ones are in the frontier. Now you can start. Now in the next step, where this tree will expand, I said you can start from, if it is clockwise, you can start from the 12, huh? So that's why next, what node will be selected? This will be selected, huh? It is. So that's why here we are selecting it and we are expanding it according to the graph search. And then we are selecting and expanding it. And this is not existed in the frontier already. These are the new ones. These are the new ones, not already visited, huh? Not already visited. So that's why you are expanding them. And then what is the turn next? Here you have to go clockwise, okay? So previously you selected this one, and now you will select this one. Then you will select this one. Then you will select this one. Okay. So now this is done. This is done. And now in the next, you are selecting this one. Now one person can say that why you are not going according to the depth first search. Okay. This question can arise. Why we are not going according to the depth first search? I told you at that time in the graph search even. It is not written here that we have to follow the depth first search. Just for understanding, I I fixed your direction that you have to go according to the depth first search. Either it is tree search, either it is graph search, so that you can understand this tree. Otherwise, you can go, if it is if this frontier is a queue, you can take it as LIFO or FIFO, whatever, and you can go according to that strategy. And then you have to draw your tree according to that strategy. Okay, you can go, because tree search and graph search is not about depth first search. Tree search and graph search, there is a minor difference between these two techniques. And what is that? Repeated search. In the tree search, you have the repetition. In the graph search, you don't have that repetition. This is normally a question in the interviews when you will go for the jobs. What is the difference between the tree search and the graph search? And only people who study this course, they can answer this question. So the difference between the tree search and the graph search is only repeated states. In the tree search, the visited states can appear again. And in the graph search, the visited states cannot appear again. This is the only difference. Depth first search, that is a strategy. That is a strategy, search strategy. It is up to you. You can apply that depth first search there in the graph search, or you can go on with the breadth first search by changing, by consider, because if you will go, if you have a queue, you can consider it as a FIFO or LIFO or randomly. So that is something different. But the actual definition of tree search and graph search is, if somebody will ask you this question, you will say that this is a search strategy. And in the tree search, we have visited states or repeated states can appear. And in the graph search, they cannot. You can give this simple answer. DFS, BFS, this is the search strategy that you can adopt. Anyhow, so here, so you can, if you are applying depth first search, then maybe you will consider something from here when you expand it, huh? But we are going with the order in which these nodes are added in the queue, okay? So initially, these four were added in the frontier. This was added first, this was second, this was third, this was fourth in the frontier, huh? And then this was added first, so we are considering it first. First in, first out, huh? So we are considering it first. So we expanded these in the next. Clockwise, but clockwise. So we selected this. This was number one. And now this was number two. So now we are selecting this, number two. So now if I will expand, if I will make this path, this node is already visited. So there is no need to expand it, okay? So that's why you are not seeing any. So that's why you are not seeing any edge between this and that node, because this node is already done, visited. And according to the graph search, we will not visit it again, okay? This node, this green is already in the frontier, you can say. Already available. This is the green one. So green one means available in the frontier. So that's why we will not visit it again. And then what? Okay, this is a new. So okay, draw it. This is a new one. Okay, so this draw it. And now what is the next node? This one. This is the number 3. Select this. I can draw this edge, but this node is already visited, so I will not draw. And similarly, this is the new one. This is the new one. Okay, then expand it. And this is number 4. So select this. I can draw, but it is already visited, so leave it. Similarly, leave it because already, so this node is already explored, huh? Or you can say already in the frontier. And now this node, this is a new one. So, okay, put it in the frontier or make a line here, make a path here. And then in the next step, if this is the goal node, huh? If this is the goal node, Then in the next step, so this is number one, this was number one, this was number two, and then when you added this, so if you will go this clockwise, this is number five, huh? This is number six, this is number seven, huh? So now five, now the turn of five, so you will expand this in the next, in the step D, you will expand these. And after five, the number six, you will expand this. You will not expand this because already visited, huh? And then after six, you have the seven, this one already visited. This is new one, so expand it. In the next diagrams, okay? In the next diagram. And after seven, what are the new nodes? So after this, in the next step, you have the in the next step you have this. This is already done. This is the number 8, and this is the number 9. So you will select this. In the next diagram, it is already done. It is already done. So no expansion. Also, no, it is a new node. Oh? It is a new node. So you will do this. And after 9, so this 9, this is done. This is done. This is a new node. And after that, you will do something with this node, something with these node, and at some point you will reach on this node or this node. And when you will expand that, you will reach on the goal, huh? In the next steps. I'm not drawing all that stuff. I will give you as a question. Okay. That is easy. That is not difficult. You have to apply just the graph search, okay? So, okay. Search strategies. Let's see this slide. I don't know what will happen, but let's see that. Search strategies. So now you understood that here, even in the graph search, depth first search or breadth first search or any other strategy, we can apply any other strategy, because this you have seen something here, that how we are selecting these nodes for the tree, how we are selecting. And you now know that if I will go with the depth first search, then I will consider this tree that I will select always the left one, huh? And if I will go with the breadth first search, then I will select this one first, and then this, and then this. Breadth. And then the order, the selection of these nodes can be different. And for depth first search, this selection of the nodes can be different. So for each search strategy, the selection of the nodes which will expand in the tree can be different. Can be different or not? In the depth first search, you are selecting a node always from the left, huh? In the breadth first search, you always select the nodes breadth-wise, left, and then not in deep. In the depth first search, you always select the node in depth and always on the left side. You can also select the nodes in depth first search on the right, but depth, always depth. You will go first in the depth, huh? Because this is the depth first search. And similarly, what I'm saying, that if you have sorry for this bad drawing. So in the depth first search, you will go in this direction in depth, but you will select the left. Somebody can ask you, redesign this depth first search, go always on the right. Go always on the right, but in depth. So that can all, this is also a depth first search, but your direction is rightward. Similarly, in the breadth search, you can select this one and you will select this left and then its neighbor and then its neighbor. This is in the breadth, width wise. Huh? You can also start from the left or you can also start from the right and you can move towards the left. You can, it's up to you. It's up to you. You will fix one direction and you will go in the whole execution with that direction. Okay. With that direction. So depth first search in the depth in the DFS you are selecting nodes in the depth and always on the left, and in the breadth first search you are selecting a nodes on the left but on breadth wise, and in some other strategy you are selecting some nodes maybe according to the cost. If the cost is there, what is the cost of the node? What is the cost of the node? Here in this the kilometers are given, we can select according to the kilometers with the minimum or with the maximum. We can select any node. So what is search strategy? Picking the order of node expansion. Which node you will select to expand? This is called search strategy. Okay. In the search, which node you will select to expand or to execute next, this is called search strategy. And from this search strategy, every search strategy normally have a different tree. Okay, can have, yes, it is true or not, because node selection is different. Are you understanding what I'm saying? So based on the selection of nodes, every search strategy is different from the other strategy, and we can evaluate these search strategies through these four things. We can evaluate these strategies through these four things. And what are those four things? Completeness, optimality, time complexity, space complexity. Time complexity and space complexity you already know from the course of algorithms, but this completeness and optimality, maybe these are the new terms for you. Is it or not? So what is completeness? You have to check these four things to evaluate any search algorithm. Okay, search strategy here means search algorithm. How you can evaluate a search algorithm? By using these four things. And then you can finally decide that this algorithm is better than some other. But you have to find your answer through these four things. What is completeness? The meaning of completeness is this, that your algorithm will find a solution or not. If your algorithm will find a solution, that solution is wrong or correct, that is not the question. Okay. If your algorithm is able to find a solution, then that algorithm will be called a complete algorithm. Okay. Okay. And if some algorithm will not find a solution, incomplete or incomplete. So this is completeness means. Optimality. Normally, algorithms find more than one solution, but there would be one best solution among those available solutions. So finding that best possible solution is called optimality. And then that algorithm would be called optimal algorithm. If your algorithm is giving you the best possible solution, then that algorithm is optimal, otherwise not. And we have to find the optimality of the algorithm also. Time complexity, the algorithm will take how much time, and space complexity, how much space that algorithm will take. So from the algorithm that we are going to see next, we can see how much time it will take, how we will find this answer. We will see that how many number of nodes are generated or expanded. In other words, how many number of nodes are in frontier or in explored set. Generated, these are the things which is frontier. Expanded, this is what? The explored set. So you have to see how many total number of nodes are expanded or generated. And whatever would be maximum, you will take that value for the time complexity. And space complexity. What are the maximum number of nodes that are stored in memory for that algorithm? And you will check the data structure, whatever the data structure you are using here. Frontier is a data structure, Q. Explored set is a data structure. And then you will see what is the maximum space that data structure is taking. And again, you can find that space by the number of nodes. What nodes that Q is having, huh? What number that Q is having? You can count the space by considering this maximum number of nodes in that memory, in that data structure.
The number of nodes in the data structure plus the explosive, because they are all stored.
You will see explore set and also the frontier. Whatever is maximum, you will have to take the maximum value, because the lower value normally you ignore for finding the complexity. Have you studied this or not in the course of algorithm? How you can find a complexity of any algorithm? Have you studied something? How you can calculate? Normally you write all the values and then you will keep only the maximum. You normally ignore the lower ones. Same approach is here. Frontier is the last point. Explore set is the previous, one layer before, huh? In the tree. If you will see here, frontier is the next layer. Explore set is one layer before, huh? So always frontier would be in a maximum position. This is not true, but normally frontier is something the next level. When it will come, you will see. So then normally in most cases you will have frontier, the number of nodes would be more in frontier, not in explored set. In most cases, it depends on the search strategy. You will see how we will use that concept. You will see how we will use that concept in finding, in evaluating these search strategies next. And then time and space complexity. So when we will measure this time and space complexity for the algorithms which are coming next, these one, BFS, uniform cost search, DFS, depth limited search, iterative deepening. So when we will calculate the time and space complexity for those algorithms, we have to consider these different terms. There would be B that we will use in those algorithms for calculating the time and space. We will use this B, we will use this D, we will use this M. And what these terms are, have a definition here. B would be what? B would be the maximum branching factor of the search tree. Maximum branching factor. What is that one? If you have this tree, what is the biggest branch of the tree that you have here, that you are seeing here? What is the biggest branch? CBU. CBU is containing 4 children and this Arad is containing 3 children. Branch of the tree means this, a node which is expanded. And here a node is expanded with 3. Here this is no expansion. And here this Arad has 3 and this CBU has 4 children. So this is one branch. and this is another branch. So the maximum branch is this one because it has more number of children. And here the tree is not complete. If the tree would be complete, then you can see then maybe some more will come. So this is called B. So the value of B for this CBU is 4. Okay, branching factor. What is the branching factor? What is the maximum branching factor of this whole tree? 4. And now D, what is the depth of the least cost solution? Depth of, yes. There may be some teacher outside. Open it. Yeah. So if we have a tree, what is branching factor? Now you have seen the branch with the maximum number of children is called the maximum branching factor. You will have some branches with factor 2, you will have some branches with factor 3, you will have some branches with factor 4 or 7 or 8 in the tree. So the branch with maximum number of children would be called maximum branching factor of that tree. And we will represent that with B. And what is D? D is the depth of the least cost solution. Least cost solution means the optimal solution. The solution with the minimum cost. Okay? With the minimum cost. For example, if you are going from Arad to Bucharest, the path with the lowest cost is called the least cost solution. And we will represent that with D. So depth of the, what is the depth? For example, here, the least cost solution is this one, This one is the least cost solution, we are saying. And then what is the depth? Depth is, okay, on the initial node, when you are on the initial node, the depth is 0 because you are at the water level, And then this is depth 1. This is depth 2, depth 3, depth 4. This is called depth, This is called depth. And we will represent depth with D. And similarly, M. M is what? Maximum depth of the state space. Here we are not talking about the depth of the solution. No. Maximum depth of the state space. Maximum depth of the state space. So maybe, I don't know, maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Maybe this one is the maximum depth, So we will represent the maximum depth with M. And we will see these algorithms in the next lecture, okay? Inshallah. So I'm stopping here. Okay.